Welcome to my SolidWorks flow simulation goals and convergence presentation. My name is Andrew Potter. I am a CSWP in flow working here at MCAD Technologies, and we're going to do a little bit of a simulation here with an open channel, not open channel, rather closed channel, where we're going to have a sudden expansion inside the channel, and we want to see how the water is going to behave. Now, overall, this channel is a rather large setup. If you'll see here from our sketch, these are given in meters. So this is, a decent size and scale for our setup here. What I've gone and done is just set up some very basic initial conditions for this, this study here. We're considering gravity because we want the pressure gradient of the water. My water in this one is going to be 20 centimeters deep, so there is actually a little bit of pressure consideration as far as the flow is concerned. It's an internal study because I've made my box closed, and therefore the volume needs to be an internal one. I've told it to exclude cavities without flow conditions. It doesn't really matter. There's not anywhere that doesn't have a flow condition. But moving on, for my fluids, I've obviously just selected water. I'm not telling it to look for cavitation. I don't expect any of that, and I don't want to slow my simulation down by telling it to look for that. From there, I've given my walls for my default condition a roughness of 150 micrometers, however you want to say it. That's to allow a boundary layer to develop on this. If I had specified 0, there'd be no boundary layer growth or any of that down the channel. And I want it to have a little bit of resolution difference, and I want to actually try to resolve boundary layers. So I gave it a little bit of a roughness, and by a little bit I mean a decent amount. And then I've come over here, and in the initial conditions you can see I just have STP basically for my pressure and temperature. No initial conditions, nothing like that. Okay. From there we go. I've gone in and set up a couple studies where they all, did it go past it? It did. There we go. So I've set up a couple studies where on the first one, I've set it to just do the auto setup. Do it by travels, do the automatic convergence, let the solver figure out how long the solver should run for. Another one I've done is I've given it a fixed time window. I looked at approximately, just from rule of thumb, basically how long one of these solves might take if the solver was just by itself, and I gave it a CPU time equivalent. That's a 15 minutes, 900 seconds. For my third one, I gave it goals to acquire and used all of them for convergence instead of travels, iterations, or calculations. For another one, furthering the curve on that, I went in and did a little back of the envelope. I wonder what my average speed in the channel should be given my pressures, and found that maybe I should look somewhere around 8 to 15. So I started at the lower end, and I just gave the entire channel a forward velocity of 8 meters per second. The idea that I was shooting for with this is that if I set it all the way down or all the way up to an average condition, the solver doesn't have to allow the entire body to come up to speed. It's already moving, and it can iterate from that value instead. So, and then just for a little bit of fun on the side, I also did one where I told it to refine the value once. So I told it that once it refines my computational domain, it needs to then either satisfy the travel requirement or the goals requirement, one or the other. Then I did, for my second one, for double secret refinement, I told it to do 2 refinements, but then I also specified that it needed to do both all of its travels and all of its goals, not one or the other. So from there, you're probably wondering kind of how this all went. I'm going to bring us over to the SolidWorks itself here. Missed it. There we go. Apparently I suck at this. There we go. So this is our actual model. if you just wanted to have a visual picture of what we're looking at here, thought I'd actually show you the channel model. And as you can see from our study, we have some goals here. I know it says no goals, but if you remember in my flow simulation here in calculation control options, I told it that I don't want to consider the goals. They're for information only. I'm just looking at them while the solver continues, and I'm not actually going to consider them when I am, or when the solver is trying to converge. Now, as you can see, I didn't specify any interesting boundary conditions. I just set a pressure on this face of 2 atmospheres and an environment pressure on the other side of 1 atmosphere. So a little bit of hydraulic head on water pushing it through an expansion duct, right? So from there, I want to show you what the solver windows look like as I finished each one of these. So I'll go back over here to my PowerPoint. So this is with no goals. You can see I have a velocity across this is right after the expansion, and this is right before the expansion. These are my pressure and velocity charts. If you look, you can see my convergence numbers, and you can see that this solver finished in approximately 11.5 minutes. Comparing that to given just straight up CPU time, it finished in exactly 900 seconds and 1 second to finish. So 15 minutes on the dot, and it went 370 iterations. When I gave it goals, however, this thing converged in 3 minutes and 44 seconds, which, you know, that's a pretty significant difference between 11 minutes and 3 minutes when the solver decided when it was done versus these are the quantities I care about, make it so, converge around these, and you don't need to take it any further. And then finally, this is my initial conditions one. You'll notice there is a slightly steeper curve on the upward scale here, and we finished in 3¼ minutes, which, you know, if you were doing this in days, it scales about like this. If you were doing this in days and you had 3¼ versus 3¾ days, that's a pretty big difference in the time it takes the solver to accommodate. And so these were my refined ones. I had the mesh shown on here so you can see what kind of detail it was refining to, just to get an idea of what might be going on. So the refined on this one, if you remember, I told it to have a boundary condition or a larger boundary condition, and I told it to have gravity. So if you'll notice out here in the pressure graph, the mesh is actually deeper down here than it is up here. The boundary layer begins delaminating down here first and not up here as quickly, result of gravity on this case. And then you can see that the boundary layer continues to build, and they have a very large mesh to accommodate that, whereas the central flow, which you can also see up in velocity, is captured by this central channel. But then when I go to the really refined one, you can see that it really tries to develop that boundary layer and show all of that effect happening inside of there. You'll also notice when I go into the results that these refined meshes take a significantly longer time to solve. It should be noted that if I look at refined, we have a solver time of 15 minutes and 4 seconds, and that was with a decent amount more mesh added at 132 iterations, and then it went another 40 iterations to smooth out the cells. So not bad. It was the same as the CPU time alone, but I got much more high fidelity results. But I could have had the entire thing in 3 minutes and still had my numbers. But here in the more refined, when I told it to do 2 refinements, you can see that that brings my solver time through the roof. So I'm into the 4¼ minutes, or sorry, 4¼ minutes, 4¼ hours, which is a much longer solve time. You can tell I have a much finer gradient in all of my results. My mesh is much finer around my channel, but all in all, my results that I'm getting are very much similar to each other. So when you compare these guys on a graph, just to show the visual impact of it again, putting goals and initial conditions can vastly speed up your processing time just because the solver is then knowing what to look for. It's not intelligent enough to know that this is a channel flow and you care about mass flow and velocity inside of it, and it doesn't know that. So if you give it goals and tell it what to iterate around and refine its values around, it knows where its stopping criteria is, and it won't unnecessarily iterate trying to get other very, very inconsequential values to converge. I mean, just look, huge third of the time. So on that, I want to show you the difference in results that I got for all of these, and I have a slideshow put together for this one. It's one of these folders. So if you'll see here, this is cut plot 1. This was with goals. If you compare that with initial conditions, if you can, wow, didn't mean to click that. If you can spot the difference, it's just barely apparent down here, but there's almost nothing. This is the more refinements. You can tell that there's a big swirl, that it developed a little bit more, but nothing else really changed. This is the no goals, back to the original. This is with CPU time, nothing except that. And then this was just the simple refinement one. If we compare these, I've created a 3D plot of the pressure gradients inside the square channel. It's very easy to see the difference in resolution in how these fields are developed around the discontinuous edge inside the channel. You'll notice this one here was our goals. There's initial conditions. There's just barely a difference right here. Down here we have in more refinements, you can see it much more finely developed, that discontinuous flow around the edge, because it shoved a bunch of elements in there. This is the no goals one. It's very similar to all the other ones. The solver time, CPU time, looks exactly the same as the no goals one. And then the simple refinement ones, you can see some of the turbulent energy up there as well. But comparing these in flow streams, where we have goals, initial conditions, refinements, no goals, nothing but CPU time, and then just some refinements. We can also compare those with flow trajectories. You can see that these almost all look exactly the same. So, looking from there, what I've done next is I've drawn a line down the center of my plot. It was drawn on the midplane and drawn from the center of this 200 millimeter gap all the way down. And what I've done with that is I used the compare feature in SolidWorks. If you're not familiar with that feature in Flow, when you're working with something that has more than one configuration or more than one study, you can come up here to this flow simulation results, and you can use the compare function. Compare allows us to come in and choose what type of cut plots, charts, ISO surfaces, all of that post-processing stuff that we want, and which projects to apply it to. So in this case, I've just made a comparison of the 4 that I actually intended to try to benchmark together. The refinements one is obviously a different animal, but we wanted to, and I clicked the wrong ones anyway, but wanted to make sure that we were comparing, pretty apples to apples things. And with that, when we come out here to these XY plots, there's this button where we can save all of these to Excel. So what I've done is done exactly that. It saves them all out where it takes the data points, and you can see it takes a very extensive list of data to generate these charts. And so here we've got velocity, for example. And we're looking at what the velocity profile is compared to which one of the studies performed it. And so if you'll notice, the initial conditions, the one where we specified nothing, and the one where we had goals, all follow a pretty relatively similar curve. I mean, within 1/10 of a meter per second together around. They converge together, and almost all of them have the exact same velocity profile from that point forward. You'll notice the 2 refined ones have a slightly different and more curvilinear profile to them, but you can but that's with velocity. Pressure, you'll notice that it refines the pressure curve a little bit more, but between all of those studies, for all intents and purposes, those are the same exact curves generated for each one of them, but the refinement ones add just a little bit more detail. Dynamic pressure is the same story. We have basically everything together, convergent, and they're all the same. So if you had the choice between the nothing sketch, which is the just CPU time, 15 minutes, the no goals, which was 11 minutes, and the goals, which generated pretty much exactly the same data, you're going to probably choose the one that took 3 minutes. And from there, the initial conditions, if you'll notice, follows underneath. Because we gave it the initial conditions, it follows the one that we generated with just CPU solver time. It follows that one even more closely. And the initial conditions allows us to save CPU solver iterations to solve for the little dynamic effects that adjust these tiny little parameters a little bit versus spending iterations trying to just develop a big flow field. Now, when it comes to things like vorticity, which is the next chart I'm going to show you, this is one of those ones where a result is going to be significantly different because of your refinements. Almost all of the flow in the channel is going to be exactly the same, except for the fact that there will be a difference in the way the turbulent energy dissipates across the cells. It's a bunch of really intense gross math that I don't feel like you want to go into, but suffice to say that when you're looking at vorticity, the extra result in there allows the turbulent energy to dissipate in a much more linear fashion. And so we have a much lower vorticity, even though overall the element is going to have more vortex at the bottom of that square channel. Our line that we're looking at across the center where the flow profile is, it's not included in that vortex nearly as much, so it loses in this line a lot of its vorticity. If we were to look at a chart of a cut plot of vorticity, you'd see a high area of vorticity underneath the square channel in the refined copy. So with that being said, I'll go back here to my PowerPoint. That's all I have to add about some boundary conditions and convergence and goals. If you have any questions, I'd love to hear them. If there's any comments, also open to all those. So just let me know. How's it on that end, Brandon?
It was a good presentation. I do have a few questions.
Fire away.
So the first thing was that compare feature I never knew of before, so that was really cool.
Okay.
And then another thing is what's the difference between a boundary and an initial condition in one of these studies?
Okay. So a boundary condition is something that the solver is trying to enforce that is happening, right? If you set a mass inflow at one end, it's telling it that mass needs to be flowing in at that. The initial conditions are much more for setting up the problem so that it doesn't have to do as much work. Think about if we were doing like an electronics enclosure and we knew it was going to be operating in a 50°C air environment. Well, we'd want to tell the initial conditions that everything, the solid and the air, is at 50°C so that we don't tell it to try to heat everything from 20°C all the way up to 50°C through iteration and then try to solve the flow sim. If we specify it ahead of time, the solver can spend a lot more of its resources trying to get the fine detail in there.
Okay. And with an initial condition, it's not going to change throughout the simulation? Or will
that is just the start parameter. It's it has nothing to do with it's not like added into the flow field, right? If you told that one side had a pressure and like if you noticed, I got the same exact velocity profile through the whole thing. I just got to it faster.
Okay. So I guess if I were to take, say, a pressure on one side, and then maybe like another pressure on the other side, if you put an initial condition of the pressure, or can you even do that?
Yeah, if you, I'll show you on the SolidWorks side of things. For your boundary conditions, let me exit my compare here real quick. for your boundary conditions, if you want to, you can specify all these mass flows, volume flows, anything like that. Also specify them as pressures. And then if you want to improve those in the initial setup, general settings, initial conditions, you can also specify a global pressure. So if you're expecting flow in the pipe or something like that to be at somewhere around like 2 atmospheres as average, then you could set it that way, and then it would propagate the pressure away from 2 as opposed to trying to build up from 1 or wherever you're at.
Okay, I see. I guess that's useful, but in my problem, it's not anywhere near close to what actually happens. But I'm just trying to figure out, well, for my problem, because it's essentially you have a valve, and then once the valve opens, you've got an accumulated pressure behind it, with atmospheric pressure in front. And essentially, I'm trying to figure out how that accumulated pressure behind will flow through the system. It's just a bunch of pipes and connections and fittings. Flow through that system, and then essentially it's going to hit a piston and push the piston up. The only thing that I'm having trouble with now is that I haven't come across a way to simulate the motion of the piston with this flow simulation tool. And
the motion of the piston is going to be an incredibly hard thing to solve because that is a moving mesh boundary, which requires a transient solver that's also a geometry update. So is the piston in your example, is it like pushing against something with a known load, a spring, something like that in a valve?
The piston is, well, there's the valve is piston actuated, but that's not, I'm simulating it after that has been opened.
Okay.
The piston that I'm dealing with is the only thing that's only forces acting upon it are there's rods that are connecting to it, so there's a mass, a gravitational force, and then there's probably some sort of air resistance on the top, but that's about it.
Okay. One of the ways that you can simulate that, if you know how the valve is going to be opening, like if you have any data about the pressure profile leaving the valve or anything like that, one of the ways I suggest doing that is like for our total pressure boundaries. Have you ever messed around with using the dependencies?
No,
or
I have
formulas?
Not. I have not.
That's one of the ways that I found where you can like write a function that is like the pressure starts at a level and then decays out as if the piston, you can have it be the opening, and then you can have that be as if the piston was allowing more or less flow through, right?
Mm-hmm.
And so if you put in a formula, you can, usually the way I do it is I'll put in a curve that I want, and then I'll write it in Excel and then curve match it and pop it in here as a formula, because this accepts basically everything in the formulation that Excel does its equations. So.
Okay, I see that. That's helpful for sure. Just trying at this point, I'm just trying to figure out what type of, or a back of the hand calculation for a boundary or boundary conditions that I would be getting. Because I've been running through just kind of to try and get some sort of like a mass flow rate, just based off of a pressure difference, essentially.
Yeah, and if you can get any data for the mass flow rate, you have much more power in how you want to set up your flow fields. Because now you can even, with your mass flow, you can have it be like if you know the flow profile inside the pipe before it's leaving, you can even specify that as a table, formulas, things. If you have radial flow ones, all of these have incredible amounts of flexibility in their dependencies. So.
Okay. And then did you say, so if you do have that moving mesh solver, and it will actually account for the movement of this piston, essentially? So go ahead.
Yeah, that's beyond the capabilities of the SolidWorks flow.
Okay.
It has to be something that's a rotating mesh in order to capture a moving mesh.
Okay.
But you might be able to have a rotating mesh that, like, I know that I've seen that done for a ball valve. where they had a section that rotated, and they had the section inside rotate into position, and they had it really, really, really tiny, really, really small time steps as it rotated into position. And then by solving it with a transient analysis, which the time dependency one, where you can add time steps, you can tell it to, with rotation enabled, yes, I know, and we use the sliding, we can have the one piece of the valve move and have a really, really, really fine time step to capture the valve start from closed and move to open.
Okay. Okay. So
but having a physically translating boundary is difficult. However, one thing you can do if you haven't used it before, let's say you have a valve with a piston. I don't have a model here on hand, but if you right-click on your goals or on your study and come in here to parametric studies, you can do a study where if you have like a set of positions for the valve, right? You could set up an assembly with a mate of that piston moving inside of the valve, and then use this guy right here, a dimension parameter, or then you'd click on that mate out here in your mates if it was in an assembly, and it would add that parameter, and you can move the piston up and down inside of the valve, have it solve each one of the iterations so that you get an idea of what the flow field coming out of the valve looks like each time. Take a cut plot with the Excel data, take the averages, write that into a curve, and then write that as a transient boundary condition coming out of the hole.
Okay. Okay. And so this is with that parameter. So say I think what I've got is I've got a limit distance mate in there.
Yep, that's exactly what you'd use. And
so with that, it will actually will it measure it at each distance in the?
Yeah, what it'll do is I'm in a what in here, what if, which is what we would want to do, where you tell it input parameters, and then you'd have all the things that you want to measure on the other side of this one. So in this case, you'd be like, I want to know the average velocity flowing out the valve when the piston is here and when the piston is here. And then you'd output all of those. And your scenario, when you have your input variables, you can, in this case, you can also do it through goal. But either way, at the end, it'll pop out. It'll solve a series of flow simulations at each one of those values, and then give you all the results at the end.
I see. Okay, that helps certainly. And the other thing that I don't know if SolidWorks can handle this or not, but within that mate, the piston itself is essentially it has two annular faces on it, such that and it sits into a manifold such that once you've lifted the piston a certain amount of distance, the surface area of the piston increases by over double, and in a very almost instantaneously. And so I ran a few studies, or just some simple calculations with the FOSIM at certain positions, but because of the huge expansion of surface area, the forces are drastically different. But because I don't do that transient between the two, all I can do is just extrapolate, or I guess extrapolate or interpolate between the two forces to figure out what it would look like.
If you do it this way with the optimization or the what if, especially the what if, it'll do the study, and you can be like, I want you to solve for the piston in this position to this position with this many steps in between, and just give me the result, and it'll make that chart for you. So if you know right where that fine line is, you can set it to run the what if right in that area.
Okay, yeah, that's certainly what I was looking for.
Yeah. Great. Well, thank you for attending, and have a nice day.
You too.